So good morning, welcome to today's lecture of the Advanced Artificial Intelligence Methods for Chemistry. So today I want to do recapitulation, but quite detailed, about how we go from recurrent neural network to transformers. There are a few, or actually several crucial steps, and it's important that you understand the logics behind all the steps. And then I will move to a very broad overview of graph neural network, and also we'll talk about general point of representations in deep networks, and the analysis of this representation by means of variational autoencoders that are actually the entry point to kind of generative AI, even though I will not go into more details about generative AIs than variational autoencoders. Okay, so let's see the pathway from recurrent neural network to transformers. And to do that, we first need to kind of remind ourselves why recurrent neural networks are an interesting model class, or an interesting kind of variant of neural networks. So we are addressing the general modeling problem where we want to predict a quantity y, could be a scalar or a vector, could be a classification, that depends on some order variable, so time, especially because many of the actual problems come from series in predicting the behavior of time sequences. So this property, unspecified property y, as a function of time, depends on some input at time t, an input at time t minus 1 dot dot until some time t minus n, where n is a parameter of the model. So we are looking at all time steps between the current and n before the current time step, and this is the general setting of finite response systems, which is a broad enough class, going from economics to meteorology and deep into physics, of course. And then we also looked into the kind of generalization of these models into the infinite response systems, where we just say that the output at time t is depending on the input at time t, and the output at just the previous time steps. If you write this in this recursive way, basically you kind of accept that the output at time t can depend on the whole history, will depend, and of course with different weights in different time step, on the history of the whole process that we are trying to model. So this is the infinite response system. And then we also looked, these are all steps that I hope you can keep in mind for nomenclature, if you here talking about this kind of modeling, and also to orient ourselves on what we are actually modeling here with neural network. So from this representation, we go to the so-called state space model that kind of decouples the kind of time evolution of the model itself from the actual output that we are interested in. So let me just write, I mean, you have seen it already. We define a state variable h, that is a function of t, of time, and this is a function of the input at the time t, and the state variable, so this is the recursive part as well, at times t minus 1, and then we say that we have an output of interest at times t that is a function just of the state variable, also called hidden state, so where the h comes from, at the same time t, right? So the recursivity is in the evolution of the state variable, while the output depends on the state variable at that time. So this, as I say, again, this is written in a very abstract and formal sense way, but keep in mind to fix the ideas that we are talking about some dynamic system. So we are looking at the evolution of a system of atoms, and the H, the state, is the collection of all the position and velocities of our particles, together with the information about the nature of this particle, their atomic number, or anything else that it is important for the model interaction that we have there for the actual time evolution. And the output would be some observable we are interested in, some dipole moment, for you know, infrared spectroscopy, or even monitoring variable like the total energy, and so on and so forth, everything that you measure and or monitor during a molecular dynamics simulation. So that would be, I think it would be helpful, given also that we are in a chemistry kind of the department, that we have a kind of a natural recurrent model that we model in this way. So all this that I've written so far doesn't really kind of how to say, that doesn't need to have neural networks, right? So people have been modeling this kind of time series, time sequences of events without neural network. However, we are in an artificial intelligence course, so we want to basically see how this relates to neural networks. So especially the state space model is the natural setup for modeling with neural networks. So SS model, or model class, if you want, into recurrent neural networks. So basically we would define a network that is exemplified by just the square, the rectangle here, that accepts inputs and has an output, say the state variable, h say 0, and also the actual output we may be interested in, and then it gives the output to the next instance of the same network that will have a different input, and so on and so forth. So there will be an h1 and then y1. So as I've shown already a couple of times, the neural network is an actual neural network, so it could be a multilayer perceptron. The new thing with respect to just any multilayer perceptron is that we accept as input the output of the previous step, right? So the simplest scenario would be that you just concatenate the h0 and the x1 to the input of the network. Of course, I'm always I mean, I'm not always commenting that you need an initialization, right? So the network always expects to have an hidden state from the previous step and an output and an input from this step. And this is just a parameter, this h minus 1. Let's say you're training the network and you just start with this state from the beginning of time and then do the iteration. But so this is the connection between this response system and neural networks, and recurrent neural network. Now we so that we go from so the kind of simple architecture that I have sketched here is the kind of one-to-one architecture, means that you have an input x0 and you have an output y0. So at each time step you have an input and an output, and you have all the machinery of propagating the hidden state. So imagine that you want to do, yeah, I don't know, you have a movie, and so each time you have a new image, so each x0 is actually an image, and you want to classify each image if there is anything in that image, like if you can see that there is a formation of some structure in some microscopy image or not, or you're measuring some observable out of that image, or again, think about your molecular dynamic, and you have this one-to-one kind of model. And then we say, okay, imagine that now you want to have one input, but actually many outputs. So in this context, keep in mind that in a sentence, as in a language, a natural language sentence, is, or basically, well, can be thought as a time sequence, right? So it's just a sequence of symbols or phonemes, if it is said aloud, where there is clearly a correlation between the input and the output sequence, and there is a correlation within the symbols in the sequence. So it's really a sequence as we have in anything that it could be trajectory in physics and so on and so forth. So the one-to-m, the example could be image captioning. Now you have again a time series of images, and then you want to caption each of some of them. And this would be an example of one-to-many. And then we would have, say, the example of many-to-one. So the one part is always like I predict a number or a classification. And then the many, when I put the many, is always, not always, but in this context we think about a sentence. So basically think about a sentence or whatever, paragraph, so kind of complex set of sentences classification. So you want to classification. So you want to assess if a paragraph talks or not about a certain concept. And then the most general case would be, you can guess it, many-to-many, and think about translation. So that you have a sentence or a paragraph or a book in one language that you want to translate into another language, but then of course anything that is prompting a language model, right? So then you would ask something to a language model in natural language, and you get an answer in natural language. Could be more complex. You give natural language n images and tables of data and so on and so forth, and you get as an output some description, some images, some tables of data and combination of these things. So we now focus, for going into transformers, to this many-to-many kind of scenario, and we kind of step by step go from this recurrent network, where we have the network that has several kind of recurrence instances, so like your time, so 1, 2, and then dot dot until some final time, and then this goes into some kind of state where it starts. So the network will always have some kind of output, but we basically neglect in the first part when we give the input. And then we start translating, and then we have also here several states, and so here the idea is that we call it S1, S2, S3, dot dot dot. So I change the letter from H to S, and then the input here is not important, except that at some point we need a special input that is called start of sentence, and typically this is end of sentence, to say, okay, we have finished with the first part. So what is this first part and second part? So this part here is called the encoder, and this part here is called the decoder. And now this many-to-many kind of example can and should be can be treated with a recurrent neural network, but in this kind of architecture that I have sketched here, that is a kind of state of the art before people started evolving from attention mechanism to self-attention, so transformers, as I will show in a second. So basically the communication between the encoder and the decoder is this final hidden state that contains the whole encoding of the input, and then triggers the decoding from the decoder. And so again, you have to think at this hn variable as a multidimensional vector, so it has as many dimensions as needed to encode the signal, and so it is such that it is a numerical representation of the input that is suitable for kind of producing the output. So the problems that we see when we have this kind of architecture is that, like the general problem is that we call it problem 0, because it's kind of like the elephant in the room, so it's kind of obvious. A lot of info is in this hn, so the final representation of the sentence. And to kind of specify better what is the technical problem, because of this lot of information, is not really a problem in itself, is that so the memory of say x0 through h0 is vanishing, kind of thing, almost lost in hn, especially if n is large, right? And symmetrically, the memory of hn in the decoder vanishes in S, I don't know, P for P for large P, right? So at some point, the only entry that we have in information from the decoder is then passed through the different states of the decoder, and so we would like to kind of keep in mind the encoding and not just get it dilute while you go through the decoder session. So these problems are addressed in a compelling sequence of kind of improvement of the architecture. So first, we introduce the context. It is a variable C, and it is a function of the time, and henceforth I use the time index for the decoder part. So whenever I say time, so there is for each instance of the decoder there is a context variable, and I mean, in the general case, in any case. So we say first of all that we want to have this context variable is a function of in principle all the HI, all the states in the encoder. Right, so H is always the state for the encoder, S is the state for the decoder. We like to fix the ideas. We could say an example could be a C context that actually would be the same for C of T is actually always the same. Nothing forbids us to say that it's always the same for each time, so it doesn't depend on the time in the decoder. And so the simplest that one can imagine is the average, right, of all the HIs in the encoder, right? So then we say so basically. The idea is that such a network would have say the encoder part, and then there would be a variable C that it is defined as some function of the HIs, and then this variable C is given as an input to each instance. Sorry, I should change the color to make it a bit more consistent with the above. So this is given as an input to all the steps in the decoder, while the decoder is accepting, say, his so S, and then for example, each input would be the output of the previous step, right? So there would be this kind of communication. So each, and it could be also the passage of some state variable, for sure. The key point is that we define this context that it is given at each time step in the decoding part. So that's the general idea. The most general context variable could be defined, let's say, at this level, at this step, before we complicate more the matter, is that we have, guess what, some linear combination. It depends on the time t of the HI, right? So we sum, and we just request that this wi for each time they are bigger than 0, and the sum of this I is always 1. So we treat them as a probability. Basically what we are saying is that the hi, the hidden variable in the encoder, for each time step, there is a linear combination with different weights of this hidden variable in the encoder that gives rise to the context variable for the decoder, right? So we construct these self-normalized weights. This is important because it comes over and over during the idea of building a transformer. So we start saying, okay, let us define first any function that is a function of the input, so the state variable, and the output in the other of the so the state of the decoder, and to fix the idea, this could be as simple as just say a scalar product between these two state vectors, and then of course, especially because these two state vectors do not need to have exactly the same dimension, we have some kind of matrix that maps one into the other. So this could be a kind of linear transformation, and then we since we want these quantities to be normalized as specified, so the weights would be, for example, a soft max of the AI. So that means that I mean, just as a reminder, we always take the exponential of this AI, and then we normalize by the sum of the exponential. So we can interpret these objects as probabilities. They are always bigger than 0, and then they are bigger or equal to 0, and they sum to 1. So this would be our general definition of a context. And now everything here is specified. The point is that we would train our model so that we learn these weights that are a function of, so they connect the hidden state I to the output T, right? So there would be, in general, a matrix of these weights, and we would learn it by just giving examples of our data. This is always the same story for machine learning at the end. So this was step 1. Step 2, to go towards transformers. We just say, I mean, we essentially complicate the model by going from this kind of simple definition of these AIs to the CI. We go from this to the so-called query key value approach. So basically we say, first of all, we define new variables, a variable ki, that is a function, again a linear function of the state hi. So there is a transformation matrix that is specific to this k variable, and then we have a vi that is a transformation, or another transformation of the hi, v. On the other side, on the decoding part, we define a q query variable that is a function then now of t. And would be some kind of projection of the state of t minus 1. So there is extra complication. So basically, if we think about our network. So recurrent network sketch, so we would have H0 and H1. For each of them there would be a key and a value 0, a key 1 and a value 1. So these are kind of transformation of the state that we have in the encoder. And then let's say dot dot dot, we have the decoder and the state S1 would have now our output 1, but also our query 1, right? And apart from that, we do very similarly to the step before. That's why I built it this in step by step. So basically now we say that the AI, in order to build, well, let me invert so that you follow better, hopefully. So the context variable would be now a sum of the weights similar to the previous case, but multiplied by the V value kind of variable, while in the previous case it was the context was multiplying directly the state variable. So we allow a bit more freedom by means of these projection matrices. And then we say, okay, the AIs are now, so EIs function of the K and the Q. And then the WI would be the softmax of the EI. So you see the function here was a function, the AI were a function directly of the state in the decoder, and the encoder and in the decoder, and here they are function of projection of the state in the encoder and the decoder, right? And then whatever is learned here by softmaxing, then it is taking a linear combination of another projection of the encoder, so of the state of the encoder. So here is a little bit of attempt at explaining the nomenclature. So we basically say that we query our state here, and then we look for something similar to the query by means of a key, and then we read the value, right? So basically we interrogate the state variable in the encoder if there is something similar in some sense to the state of the decoder, and then we read out some kind of values in order to create this context variable that triggers the next step in the decoder. And in practice, so basically we allow a larger representation, larger dimensional representation in the encoder and decoder, so the H and the S, and then we just look at a subset of this representation, some subspace, so a projection into some subspace, so that we can look into different things. And again, here it's probably useful to keep in mind that you could have a sentence and you would kind of look for at the same time grammatical kind of features of that encoding of the sentence, and you would look also at semantic kind of features. So you need different kind of ideas here. The next step is just a minor complication of this QKV kind of technology. That is, so this would be the so-called single head attention. So QKV is also called attention. And in this case, a single head because we just ask for one thing at each time step. So the generalization is the multi-head attention. in which at each step, essentially, we now have, say, a Q0, K01, and a V0, 0, and then we could extract from the same H0 a K01 and a V01. So basically, the index at the bottom would be the same as the state, and then we allow for more of these K and values, and symmetrically we would have more of these. Better to use the 1 to keep the nomenclature consistent. So S1, Y1, and then we would have a Q10 and a Q 1, and so on and so forth. This would be kind of two-head attention, and how this combine together. So well, now we define these E terms that have an extra index dependent time in the decoder, and they are a function of the KIL and the QTL. And then we go to the WI L by softmaxing. And then we define the context with index L by means of these weights. And then essentially what is passed is the concatenation of the CI, right? So basically one of the inputs of the network in the decoder would be this C1, C2 dot concatenated. So as many C's as the heads in the multi-head attention mechanism. Now we have the, so from 2 to 3 we are just saying instead of having one attention mechanism, so we have one of these projections, WK, WV, WQ, that of course these are learned, right? So you define the size of the matrices and then you will learn them. And here you just have many of these attention heads. Now, so not much of a crucial step. The crucial step before we arrive at transformers is the self-attention mechanism. So this is important because so far we have this attention that is a much cleverer way to treat this the hidden state at each step than just passing it once at the beginning and then hope for the best. But we have still a major problem. We have a sequential kind of learning. A sequential learning, yes, but most importantly, we have the encoding and the decoding that are sequential. So one, the algorithm has to wait the previous step before it can do the next step. So we know by now that if we manage to parallelize operations, we can do it more efficiently. So the idea of self-attention is to decouple the encoder from the decoder. So, and this is done by saying, okay, for each state H0, now we define directly the K, the value but also the query directly on the state input. Then what it is done is to basically issue in this way. So I do the H1, K1, V1, Q1, so H2 for example, K2, V2, Q2, and then the query at the step 0 interacts with the key at step 0, a step 1 and a step 2, right? So and this gives rise to some kind of output. That is our E0, E1, E2. That we actually then softmax. So that we get our V0, W0, W1 and W2, of course, dot, dot, dot. So the crucial thing is that the query 0 interacts with all the keys in the input, and the same will be happening for the query 1, will interact all the other states in the input, in the decoder, sorry, in the encoder, to get these weights. And from the weights, so the weights are then combined with the values, specific value at that particular time step. So interact means that you take the scalar product or some suitable matrix multiplication. So more in symbols. So we have that importantly the QI are now projection of the HI, not anymore of the state in the decoder, and then we have EIJ, that would be the interaction, so some kind of scalar product of the, right? So we go over all the KJ for each QI, and then we softmax. Over the J. So we also write this as a attention operation of the QI with all the K value. And then at this point we generate a new variable that is called an output, O. That would be, so instead of a context, we have this kind of, we could call it C, let's call it C. It doesn't really, it's not a strong reason to change the variable, it's just that this J, C doesn't now directly interact with the decoder. We just store these variables and then they will be used for the decoding. Sometimes, if not always, before we get to the actual encoding, we go through a neural network, right? So we take this CI, that is a vector, and this is an input to a new neural network that is completely to be trained in order to give, let's call it, well, in the notes is Y. So this is the output, the actual output of the encoder, right? So we do some extra transformation of the context, and then we arrive at the encoding of a whole sentence. So this idea here is called self-attention, that builds on the attention mechanism that was a solution to the problem of these recurrent networks, that are a nice solution to recurrent problems, and so response systems that are a very general class of mathematical models for kind of analyzing and predicting a time series. Okay, I took my time to do the kind of extended recapitulation, but I stop here. So from here to transformers, the idea is basically that we have a self-attention mechanism also in the decoder. It has to be a little bit different because we have to avoid, so we have to kind of preserve the fact that the decoder does not know yet the output that is yet to come. So we have to apply another device that is called masking. So we just basically, besides this important but I would say technical aspects, the overall idea is laid out here, and it's worth mentioning that the final step, so this would be single head, and then we would have also the multi-head self-attention that would then kind of put everything together. And then once more we can look into what is a sketch of a transformer from the original publication on transformers, in which we should understand that now we have this input. The input in itself is embedded. This is typically yet another neural network, so we have some kind of representation. It goes into the multi-head attention, followed by a multi-layer perception, aka feed-forward network, and this is done a certain number of times, nx, and this is our encoding, and this is then given to the decoder that looks the same, except there is this masked multi-head attention device, but we don't have to bother. And this positional encoding is a way to recover the sequence, because by doing this operation in parallel, we have broken the sequence, and so we store somewhere in a clever way how the sequence actually works for the decoding. So this is the extended, again, recapitulation of the pathway from recurrent network to transformers. Okay, so where are we? Now I move to a new topic. The new topic is graph neural networks. And before I talk about graph neural networks, let me explain what do we mean. So why we need something now completely different or new, and why. So which kind of problems we may want to tackle. Right. So far we have been implicitly addressing so-called Euclidean data. So Euclidean data, it is a kind of posh way to say that we have data that they live in tables, tabular, and they have some concepts of distance among the data. So let me just say, in general, we would have anything that it is really a table of data. So each column would be some feature of our data points. So if you have your good old relational database, you would have individuals, and they have birth date and annual income, you know, these kind of things. Or go to physics, you will have for each item a molecule, a set of let's say components and positions and other points and other information on that molecule, material, cluster, whatever, to stay in a kind of atomistic description or any other kind of description that we may have in physics. But we would be the same kind of Euclidean data also for images. So if we have images in thinking about a bitmap, then we have still some kind of concept of distance. I mean, you have the neighbor kind of pixels, and you would give coordinates, and you will find them. So and then you could have sequences like the recurrent network that we have seen so far. Let's say if we have data with not much particular structure, we basically in the neural network, in the deep learning kind of arena, we will think about a multi-layer perceptron. If you have images, we would think about a convolutional neural network. And here we would have, say, you know, recurrent neural networks up to transformers. But so far, if we stay in this kind of Euclidean data, where essentially we define at the very beginning, before, so when we set up the problem, the kind of dimensionality of the problem. So the images have a specific dimension, the sequences, we are propagating vectors with the specific dimensions, and we have a time kind of coordinates and this kind of constraint that we have in Euclidean data. Then we have the great divide here versus known. Okay, that's not very Euclidean data, where we basically have just some kind of relationship without any specific metric in the representation, right? So the typical example would be knowledge graph. In which you want just to represent relationships among items in the graph, right? So think the not so general example of you have the painting Mona Lisa from Leonardo da Vinci, so you would have a connection. The painting is painted by Leonardo da Vinci. Leonardo da Vinci was born in Vinci, that is a city in Tuscany. Back then it was definitely not Italy, it was just Tuscany. And then he worked for a long time in Milano, and so you would have this kind of connection. The painting itself is currently located at the Louvre, that is a museum in Paris, and everything that is connected, so you want to make connections among these objects, the painting, the museum, the city, the painter, the city the painter comes from, and so on and so forth. And this would be an idea of non-Euclidean data, right? So you don't know how many of these connections there are. The painter could have moved in many different cities, that if you look into their history, because you want to keep track of something, that you have a non-specified amount of information that you want to store at the city where the painting is, and then you could look at the technology of the painting, and you want to keep track of these things, which kind of colors Leonardo was using, and so on and so forth, right? So this would be a kind of example of non-Euclidean data in the terms of knowledge graph. You would have other graphs if you want, but probably one of the most important graph that we would have now in chemistry and material science as molecules. And in general, crystals and so on, say, and crystals, can be thought as graph, right? So each node of the graph would be an atomic species, and then you would have a bond or not a bond, and then maybe you want to specify which kind of bond, and so on and so forth. So, and also here you have same thing that, not same, but a similar aspect that you don't know the size of this, so how many nodes you would have, which kind of relationships. There could be different kind of relationships that you want to treat at the same time. So definitely not Euclidean, even though don't be disguised. Of course, you can always say, yeah, I have a simulation in a supercell, a fixed number of atoms, coordinates, and so on and so forth. I can remap a molecule representation into tabular representation, and indeed you have a multi-layer perceptron that take a problem in chemistry and material science, but just wanted to introduce that you would have the possibility also to look into molecules and crystals with a graph representation. Okay, so we have graphs, right? So once we have found a way, how I will come in a second, to kind of represent our data in a graph like manner, we would like to first decide what do we do with this graph, right? So why spending time to think how to map any data set, any given data set into a graph. We would need to understand what we are actually looking for after this kind of representation. So, well, first of all, it is probably, well, not first of all, but before I go to which kind of learning we can do out of a graph, it's better to systematize what we need by graph. So basically, we have that a graph is an object that is a collection of vertices and edges, right? So graph is specified by certain number of vertices, v1, v2, v3, and then we say that there is an edge between 1 and 3, and an edge between 1 and 2, and in this not very complicated graph, we don't have the edge between 2 and 3, for example. And so once we have this kind of object that is a collection of vertices and edges, so which vertices are connected by an edge, which not, we want to say, okay, what kind of inference we can do on graphs, right? So assuming that we have a training set that can be represented formalized as a graph, and then we have some input information, and then we want to do some predictions, right? So this is what we do when we want to do inference. So we have, broadly speaking, three kind of inferences that we do on a graph. We would have the node level inference. So basically, we would have a graph, and then we have information on some of the nodes, for example. So for some of the node, you have to imagine that for each vertices we have information, right? So basically, these vertices each vertex would have a collection of information. If it was, let's say, people in a company or whatever, you would have again their date of birth, which kind of title they have, which kind of occupation, and so on and so forth. If you have atoms, again, it could be coordinates, it could be plus some other properties of the isolated atom, for example, or if there's particular chemical species as property, as a monatomic crystals, or anything that you can imagine. And then you have a node for which you have, say, incomplete information, and you want to make inference on the incomplete information. So you want to predict what is the information missing on a node, right? So so then again, it could be a property, and only on the basis of its position in the, so its connections in the graph, right? So you know that a vertex, a node for which you want to do inference is located at certain edges and doesn't have other edges. You want to make, and on the basis of which are the edges that are the vertices that are connected and which are not, you want to make prediction on that particular vertex. So this would be our node level inference on a graph. So we would have could have a regression. We want to predict a continuous property or a classification, right? The usual kind of machine learning tasks, but now it is specific on a node in a graph, and the kind of training data is different from the typical multi-layer perceptron or convolutional network and so on. And we will see in a second how this can be actually systematized. And then we have the kind of edge level kind of inference. So now we would ask, is there or not an edge between two vertices if this information is not given, right? Again, on the basis of how typically vertices look like in terms of edges, with which edges with other vertices they connect, and which other kind of vertices they do not connect. We can predict if there is an edge or not. So in our chemistry environment, we want to predict if there is or not a bond between two atoms. Typical example would be for kind of social networks or and so on and so forth. If there is if two people in a network are friends or whatever, or if somebody, so you have the graph of the movies that are liked by people. So if people like this movie, would they like also the other movie? So is there a connection between those two movies? So they are similar in some sense, because if people like one, like also the other one. And then we would have a prediction over the whole graph. Probably I would, let me say, it's the graph or a subgraph. So there is not huge difference between these two kind of differences. So if it is just a portion, so a collection of nodes, or the overall graph. And this is kind of straightforward if we think a molecule is a graph. So we are predicting the property of the molecule, of a particular molecule, based on training on other molecules that are also represented on a graph. Or in general, we want to do any prediction on an overall maybe subset of items, of vertices in a huge graph. So this is the kind of so the edge would typically be a classification. So is the node there or not? And then again, for a graph, you would have a regression classification. And an extra operation that is specific to graphs. And some graph, you ask if two graphs are the same in some sense or not, or subgraphs. So basically, you can imagine the obvious thing would be just to say you can map any vertex to any vertex, any edge to any edge, then the two graphs are equivalent or not. Typically, is to define, but impossible to actually do in practice, because you have to try all possible vertices with all possible vertices, all edges with all possible edges, to say, before you can say yes, it was exactly the same, or there was just one edge missing, otherwise they would be exactly the same, and so on. So you would like to have a kind of possible inference of matching between two graphs. That would be very very interesting in many fields. Okay, so now how do we go from a graph to a neural network that operates on graphs, right? So basically what we want to do is graph embedding. So we want to take a graph for which we have definitions. So we have the vertices, and each vertex has a certain set of properties, and then we want to and of course we have information on the edges, and then we want to represent this in a suitable way so that the neural network can do learning. And so when we talk about graphs, the first step to keep in mind is that we define. So now I go from a representation that is, partially useful, like dots and some lines connecting the dots, to a more mathematical representation that it is suitable for then doing this kind of embedding that I'm kind of foreshadowing. So we define an adjacency matrix that is as simple as, so we have nodes, so the vertices, say, arrange it like this: V1, V2, V3. So if we look at this graph here, we have, well, first of all, a node doesn't have an edge with itself. I mean, could have this kind of things, not in this particular example. And then you have the one between 1 and 2 and 1 and 3 that is symmetric, and then we don't have an edge between 2 and 3. So as you can guess, the adjacency matrix is something that has 0 and 1s, and you get a 1 when there is an edge, and you have a 0 when there is no edge. So this would be a kind of mathematical representation of the vertex of the graph. And then for each V1, imagine that now we have also features, right? So basically each vertex, we know its connectivity with all the other vertices, so it could be more here, and then we can expand the representation by saying, okay, this vertex is actually carbon, and another property that we can decide they are important to represent in our representation of the molecule or whatever. So I introduce this because we have the most important point here when we want to represent this kind of object mathematically for doing some inference. So you can imagine that so given a graph, so probably I should just copy this very, very informative graph here. We could have labeled the vertices in other ways, right? So we could have changed, instead of 1, 2, 3, we could have, given any number 1 to any of them. So basically we want the representation is invariant with respect to the order of the edges, right? So this is the crucial point, permutation invariant. So as much as when we give coordinates to an Hamiltonian in order to predict the energies, and we want the representation is invariant with respect to the proper transformation, say it's a translation invariance, rotation invariant, because we know that given a set of atoms, if we move them, so there is no external field, if we move them or rotate them, the properties, energies, forces, name it, will be independent on this kind of operations. Then we have other things that are covariant or equivariant. These are also an important concept in graphs, in graph neural network. I will kind of avoid to go into this detail because the notation would be much more complicated. Let's just stay with the fact that if we are embedding a graph in a numerical representation, this one that I have just started constructing with the adjacency matrix and just the list of operation is not suitable because it is not permutation invariant. So we need to construct a permutation invariant operation. Then if the problem stayed like this, you can build a specific operation here. I mean, of course, if it is a matrix, something related to the determinant, it is not a square matrix, so you have to invent something that is a linear combination. But okay, the key point here is that if you take linear transformations of the rows of the matrix, it is probable that we go into a permutation invariant representation, right? So let's now go and start laying down the solution. So how people do embedding of graphs. Again, it is very crucial to understand, as for convolutional network or any other kind of network, even transformers where we had this query key value, that you start from an idea that has a meaning, so the way you would do it if you had to do it manually, but then essentially you give the burden to the network to learn all the actual transformations, right? So in the convolutional network we say, okay, we have the filters. You can imagine filters like they are doing some kind of smoothing or sharpening or looking for horizontal or vertical lines, and you could design the filters. We know how to design a filter that looks for vertical, horizontal, or like they kind of enhance this kind of features in the image and kind of smear out the other features so that you could look if there is or not a vertical line in a certain region of the pictures or not. But at the end of the day, all these filters are learned in the process by the convolution network. So this is just a justification. The same is for the graph network. We build a conceptual kind of justification, and then we will end up with some matrix of coefficients that it is actually learned, right? So this is always the same story. We need also that the embedding is a size invariant. Right, so we shouldn't have a different representation for each and every graph. So that is given. So if it has more or less nodes, probably we are not very interested if we have a representation that is specific only to that number of nodes with that particular connectivity. So these are what we ask to our embedding, and how do we build it. So let's look at the more general graphs, so that, well, not so much, but just that I can lay down some more concepts that describe how we do embedding of a graph for graph neural network learning. So let's use this one. Again, of course, the labeling of the nodes is totally arbitrary. E, F, and there is also an edge here. So these are few more nodes and some more connections. So now I want to do the embedding and I focus on the node A. Then of course I can imagine a last step in which I put together all the nodes in the graph. But let's focus on node A for a second, and then let's say that the node A, its embedding will depend on, say, well, A itself, and let's say it is reasonable to think that the property of the embedding of A depend on the embedding of its neighbors. So we have A that depends on its neighbors, but not on the nodes that are not its neighbors, right? So basically, A depends on the embedding on A depends on embedding on A, B, C, D, and then imagine that you iterate. So the embedding of well, A we have just seen, but B depends on A and C. Okay, so on and so forth. So C, well, it's a lot. 1, 2, 3, 4 is A, B, E, F, and D depends only on A. So A is node is spatial, otherwise we would explode here. So what could be the information that goes from the nodes to the other nodes? So we have 2 steps. One is called message passing. And then we have another step that is called aggregation. Right? So, right, yes, these are the steps. Message passing. So, again, imagine that each node has its own state. Guess which variable I'm using. So there is the state of age, and let's say initially this representation would be exactly its list of here of features. So this would be our x for A, right? X vector now. So all the features of A describe A. And then I say, okay, so I have a vector that defines A, and then I want to do what? A linear transformation, right? So basically I say that I take H, so in general I take the H and I apply some kind of linear transformation. And this would give me the message, right? So W, well, okay, I put an index later. So I have a message that is just a linear transformation of my state H into another vector. And then I say, okay, from this, so this, if it was A, and then it would be the same for each node, right? Where this W is the same projection matrix, doesn't depend on the node A. So this is what we're trying to learn. So this is a transformation from the state that I can give as much as initially is the X, right? This is what I've written here. And then I project into some kind of message. How do I take, so I take the message for each of the nodes. So now A would depend on itself and its neighbors, so B, C, D. So what the message that is coming from B, C, D. So let's say that now the state of A now transform would be the aggregation of the messages from the neighbors. So basically I'm, say for example, I'm taking the average of the messages of the neighbors. So this would be, let's say, the eyes that are the neighbors of A, because I have written specifically A here, right? Then I probably want to divide by the number of neighbors of A to make it independent of the number of neighbors itself, and then I want to have some kind of basically the message of A itself, right? So this would be my kind of aggregation of the information. So I put together an average over the neighbors, and then I sum the message that would be consistently dimensional with the message from the neighbors from A, and then I'm building a neural network, right? So I want to include the fact that there could be a nonlinearity, so some kind of activation function that I always put as a sigma. So now basically I have gone from A, and then I have combined the information of the neighbors. But I can iterate, right? So basically the information from the neighbor B needs not to be, so it is some transformation of each embedding from each neighbor, and so I could iterate this kind of operation, right? So basically I go to some kind of H for the node I at iteration, say K, would be some activation. Let me get the index correct. So we have now the normalization with respect to the number of neighbors of I. So this bars is the cardinality of the sets, and A is the set of neighbors of A. The cardinality with this double bar, like a modulus, is the number of elements in that set. So we normalize by that. I'm constructing the formula 1 second, and then we have the H for, so I'm summing over the neighbors J. J belongs to the neighbor of I, and here I have my message kind of matrix, WM, K minus 1. So this is the transformation from the previous representation, and then I would have, let's say, another. So this is, I call it self, because it's the message from itself, let's say, would be spatial. So this would be HI, but also that is at the previous, right? So this would be more or less the most general expression for a neural network embedding of a graph. So we learn the coefficient WS and WM. So you can imagine that this operation builds a deep network that is doing this convolution operation of nodes, right? So you start from the first layer, and this is important now that you start from this input representation, X. So your H0 is X, and then you evaluate for all the neighbors this kind of message passing and aggregation, and then you do this kind of nonlinear transformation, and you get a new representation, and then you plug in the new representation for the next layer, and so on and so forth, right? So at the end, you arrive at a certain h of the last level n, that it is a vector. And then out of that, you construct a way to make a prediction. So you have a vector, and you just use it as an input. So this vector, this embedding, this representation, is now constructed to be permutation invariant, and hopefully the W's have learned important aspect of the network for the final inference, right? So you have now your H Hn for each node, and then you have to decide a way to combine nodes. Or if you want to make a prediction of the node, you already have, like, I mean, your embedding of the node, and then you can do inference on that. And to do that, you build a multi-layer perceptron having this embedding as input, and then you can make your final prediction, right? So similar to the convolutional network for images in which you the last layer was taking our embedding, so there was all the filtering on the image. Then you linearize, you make it a linear vector, then you give to a multi-layer perceptron, typically with few layers, and then you make the final prediction. Okay, the final step before I close for today, so the presentation out and course will be next time, is to just kind of generalize a little bit. So this that we have seen here is the general setup of graph convolutional neural network, where the convolution is in these operations here, right? So everything here that aggregates the information from the different nodes, and again in a manner that is independent from the nodes. So here you could have, so it's an average, so you take all the nodes equally. Other popular operators here are the maximum or the soft maximum or whatever. So basically something that depends on the nodes, but the outcome doesn't depend on the order you have given the nodes, and so you have coded the nodes and how many they are for each other node. And so now probably, since I just explained attention and transformers, you should say, yeah, okay, but maybe some nodes are more equal than others when you want to make predictions, or maybe some types of nodes, right? I mean, on some specific node, because you want to make a prediction of a class of graphs, not a specific graph. But there could be that you don't want exactly to limit yourself by having a message passing operation that is equal for all nodes. Or better, you decompose this message passing and the aggregation in such a way that you could give attention to different nodes depending on the nodes you're looking at. And so let me just write down what is the next step for the graph attention neural network. So a generalization of the above, that given the lecture on transformers, hopefully it is pretty easy to understand. So we have that the embedding machinery, so at step or layer k+1, so we have still the activation. We have our sum over the neighbors of I. We have, well, the W, okay, so we have HI at the previous layer, but now we have, so it's typically decomposed in this way. You have, yeah, probably this K, I should have used K, not K-1. It doesn't, I mean, it's just a choice on the notation, right? So it's the W of that particular layer, not of the one before. It doesn't really matter. It's just one has to be consistent. So the WK, but now we have some attention kind of coefficients that kind of possibly weight differently. So here I read it in a way so that you include also the neighbor with itself, right? The node with itself. So you have an II here. But anyway, so probably this is the neighbor star, which include also the atom. It's not important. Just have to, not to forget that there is a self message passing. But the important thing is this alpha ij, that it is constructed in a very similar way to the attention kind of networks. So you have define the Eij, that are a function of what? Of the Hi and the Hj. Typically the message coming from them, so including the K. Right? So this is of course K dependent. Yeah, this would be K, because it depends on the previous step. And then the alpha ij would be, guess what? The softmax of the Eij. So because, I mean, you see that here I have not normalized, meaning that I expect these weights to be properly normalized so that they have an average, a weighted average of the messages coming from the different nodes, right? And I learn these alpha ij's, and so also here I can have complex kind of graphs where you have all kind of information, and then for certain prediction it will focus on certain parts of the input and other parts. So the different nodes. So this would be not the most general, but a kind of proper generalization of the graph networks. And as I was saying, so basically having also the attention mechanism inside in one way or another, everything is going to be a graph network in the near future, right? So that is, one can show that convolution network are actually a subset of graph convolution network if you kind of fix some constraints. So basically we are describing the most complex class of deep network kind of architecture with graph neural networks. Yeah, so basically I stop here, and I'll see you next time for some reasoning on representation in general, and then dive a little bit into representation that are actually used in chemistry and material science. Thank you for your attention.